Team 24087.
I'm Faye Sipker.
I'm Cassidy Chang. I'm Lorinda Treadway.
And I'm the project lead, Taya Iwan. We're all environmental engineers, and our senior design project is carbon capture for algae growth.
Climate change due to anthropogenic activity has resulted in increased global temperatures, rising sea levels, and loss of biodiversity, among many other alarming issues. With carbon dioxide being the main greenhouse gas and contributor to climate change, natural gas power plants contribute to 35% of all CO2 emissions. One way to mitigate these power plant emissions, also known as flue gas, is by directly injecting the gas into algae ponds, where the algae uptakes the CO2 and the resulting biomass can be turned into various products. An alternative to this direct injection method is a new polymer composite mesh developed by Lawrence Livermore National Laboratory. The polymer mesh is developed by using direct ink writing and is comprised of silicone, adhesive, and sodium carbonate in a layer that is about 400 microns thick. The key with this mesh is that the sodium carbonate is bound on the surface. When CO2 hits this mesh, it reacts with the sodium carbonate to form bicarbonate that binds and keeps the CO2 onto the mesh. This loaded mesh is then placed into the algae ponds, where the desorption process is equilibrium driven by the rate at which the algae uptake the CO2. This is indicated by an increase in pH, and as the algae continue to take up the CO2 on the mesh will desorb into the pond as needed while maintaining an optimal pH environment for the algae. Because this polymer mesh technology is new and still being developed, the goal of this project was to perform a techno-economic analysis that looked at the feasibility of this carbon capture method. To do this, the two main criteria that were focused on were its effectiveness in sequestering carbon and its implementation costs and overall profit. The analysis also consisted of designing a full-scale system that can be sized to any power plant. For this particular design, the algae species chosen was chlorella, which also came with design constraints specific to this strain, such as growing conditions like temperature, pH, and light intensity.
Here's an overview of the process. Our design was fitted to a mid-size 50 megawatt power plant that produces about 400 kilograms of flue gas per day. Algae farming does best in warm, sunny climates, so the setting for our design is southern Arizona. At night, the mesh selectively adsorbs CO2 from the flue gas. During the day, the mesh is unrolled into the pond, where it releases CO2 for the algae. The algae is further cultivated with steady nutrient and water flow and then harvested. The harvester separates excess water from the algae and returns it to the pond. The dried algae is further refined and sold as a product. In order to understand algae growth, we have to first understand the environment in which it will grow. Being an outdoor operation, the growth conditions for the algae vary not just throughout the day, but throughout the year. Since we're able to provide the algae with sufficient nutrients and carbon dioxide, the limiting factors for their growth are hours of daylight, light intensity, and temperature. Algae tends to do poorly in cold temperatures and low sunlight conditions. To model the weather, we used University of Arizona meteorological data from 2023 in order to generate temperature and light intensity curves for an average day of each month in the year in a Sonoran desert climate. In these figures, each color represents a different season. Purple represents Tucson's wet summer months, red is the dry summer months, yellow is fall, green is spring, and blue is winter. As you can see, the highest average temperatures occur during monsoon season and the greatest light intensity and daylight hours occur during dry summer.
Since the goal of this project is to determine economic feasibility, we needed a way to accurately predict the amount of product we'd end up with and the amount of CO2 our system could sequester. To do this, we used a logistic model for the algae growth and harvested at a rate equal to half the growth rate. The result is this graph that shows the mass of algae harvested and the mass of CO2 sequestered over 1 year. These values both change monthly since the growth rate changes with temperature and light intensity. We decided to have our inoculation take place during August since it has optimal growing conditions, and that way our model will end in July. This is ideal since in practice, operations will have to shut down due to heavy rainfall. Since the monsoons begin in July, we can shut off for maintenance during that season. We start off each year with enough nutrients in the pond for it not to be a limiting factor in algae growth. However, as the algae incorporate the nutrients into their biomass and are harvested from the system, these nutrients are lost. Based on an average molecular formula for chlorella algae, we used a mass balance to determine the amount of nutrients to replace each day in order for the nutrient saturation to be maintained. Furthermore, this nutrient mixture can be blended with additional water to replenish evaporation and harvesting water losses that occurred throughout the day. The algae growth model and final quantity of algae harvested annually was calculated under the assumption of continuous all-day harvesting. A continuous flow rate of 2 gallons per minute was found to be the maximum required flow rate for the harvester during times of peak growth. The chosen harvester is the Zobi harvester from Global Algae Innovations, pictured on the right. The membrane harvester has successfully maintained the ability to achieve high recovery and produce a crystal clear permeate while reducing energy costs 95 to 99% compared to traditional methods. The harvester is available commercially, and the purchase cost of the unit is a fraction of traditional methods, with a 90% capital cost reduction. The Zobi produces 15 to 20% algae slurry retentate that does not require additional process prior to drying. The produced algae slurry is then sent through a spray dryer to remove additional water before being utilized as a product.
The algae output from our process has the potential to be utilized in a wide range of applications. It has been included as ingredients of dietary supplements or chocolates. It can also be worn as coats, shoes, and other pieces of clothing. Additionally, algae is currently being considered as a potential greener alternative to fuel our cars, with many different strains of algae being viable for biofuel production. Due to its minimal requirements for additional processing, the algae produced from our design is intended for use in shrimp feed production, so sales from our algae are based on this market. By integrating the graph from our growth model, we predict that our design can produce almost 1,700 kilograms of algae a year, while sequestering almost 900 kilograms of CO2 per year. Using these values, we can predict the sales of our design. If we assume we are selling our algae as aquafeed at the current market price of $400 per ton, selling carbon credits for $40 per ton, and then receiving $80 per ton in tax breaks, we would be earning $800 in yearly sales. The annual costs consist of energy, nutrients, and the cost to replace the mesh. In total, this ends up being around $387,000 a year, with $37,000 from energy costs, $700 from nutrients needed for pond additions, and $350,000 to replace the mesh once its absorption efficiency is depleted after 15 uses. The capital costs come from each of our equipment pieces. The dryer is the most expensive, followed shortly by the conveyor belts, the pumps, the nutrient tank, the pond construction, the mesh columns, and the harvester. In total, these capital costs come out to $118,000. Based on our design of this system, this technology still has a long ways to go before it reaches economic viability. This project serves to further the efforts of utilizing algae to reduce the impact of power plants on climate change. One day, algae may be part of the solution in reducing global carbon emissions. Thank you for watching. We hope you enjoyed our presentation.